Right. Good morning, everybody. So we were talking about implementing an array-based list in C. And so recall that the way we're going to do this is we're going to create a structure, and in the structure, we're going to record all of the information we need to implement the list. So we have here an array for to hold the elements of the list, because this is an array-based list. In our current implementation, we are creating a list of int. Later on, so I guess in the next lecture, we'll see how to create a generic kind of data structure. For now, our list can only hold ints. We've got the size of the array, right? Because remember in C, C doesn't keep track of how big arrays are, so we have to keep track of it ourselves. So the capacity is the capacity of the array. And then size is the number of elements that we've got stored in the array, or in the list, I guess. I suppose it's worth mentioning that there are some invariants on the on our members here, right? So you just like in Java, where you have a class invariant, you can have invariants in any programming language, right? So an invariant is just a condition that should always be true. So for our list, we want to make sure that I'm just going to write these in as a comment. Right, we want to make sure that array is never null, right? Because if that pointer is null, then anytime you try to get an element from the list via that pointer, you're going to end up trying to dereference a null pointer. So that's no good. Right, we want to make sure that the capacity of the array is always at least 1. Oops, sorry. Right, you might think that maybe the capacity should be always at least 0, but there are no 0-sized arrays in C. So our capacity is always greater than or equal to 1. And then finally, this size, so the number of elements that we've got in the list, should always be less than or equal to the capacity. So when we're implementing the functions in our source code file here, we want to make sure that these invariants are always true after every function finishes. Okay. So we looked at creating an empty list, creating a list that can hold a certain number of elements, creating a list by copying another list, right? And we ended up getting to the get and set functions. So to get an element out of the list, right? So we're going to get the element out of a list pointed at by t, right? And we want to get the element at that index. Right? So of course you should check to make sure that that index is a valid index. Right? So in other words, the index has to be less than the size, right? The number of elements that are in our list. And so to do that test, I'm going to use an assert statement here. So assert that the index is less than the size of the list. Right? And remember, all that assert does is that it checks that condition. If the condition is true, nothing happens. If the condition is false, and then the assert macro will stop the program at this point. Right? It'll somehow cause the program to exit at this point. Right? Also remember that you can turn asserts on and off via compiler switch. So once you've debugged your program, so while you're developing your program, you can leave the assertions. You can leave the assertions on, and then when you're done debugging your program, you can turn assertions off, and that removes the price of that test there. Once you're sure that the index is correct, you can just go into the array and grab the element at that index, right? So it's just a straightforward array access here. Set's exactly the same thing, right? You want to set the element at the list pointed at by t at that index, and you want to set the element at that index to elem. We're also going to return the old element. So again, test whether the index is valid. Right? If the index is valid, go and get the current element sitting at index. And again, it's just a straightforward array index here. Okay. Then go ahead and overwrite the element sitting at that index, and finally return the old value. If you remember, well, so if you took CISC 124 with me, we did this in Java. It's all more or less the same thing. It's just you have to, it's just that you're accessing elements via a pointer to a structure here. Right, so we always have a pointer to a struct here instead of accessing it via some sort of reference. All right, so the next methods are things like add and insert, right? And these functions can change or may require that you change the capacity of the current array, right? So if you add to a full list, you need to extend the capacity of the array and then add to the newly created array. So we need a function that can increase the capacity of the array for a list T. So add capacity is a function that increases the capacity of the array belonging to the list T, or the list pointed at by T. It returns true if we can successfully increase the capacity of the array. Right? It'll return false if you can't increase the capacity of the array. Now, all that we're going to do here is call realloc. Right? So remember, realloc is the memory allocation function that reallocates an existing block of memory, right? Either increasing or decreasing its size. Any elements that were in the original block of memory get copied into the newly allocated block of memory. So all we're going to do is try to call realloc. So remember how realloc works. You pass it a pointer to the current block of memory that you wish to reallocate, and you tell it how big a block of memory you would like. Right? Remember that the size of the block of memory is in terms of the number of car. Right? So we have to multiply by our element size here, right? Because we have an array of int. Now, how much capacity should our new array have? Right? Well, it needs to have the current capacity, right? But it has to be bigger than that. And so the usual thing that you do is you multiply it by some scalar here, some number greater than 1 here. Right? So I'm just going to double the capacity of the array each time. What you don't want to do here is you don't want to increase the capacity by 1 every time, right? So if you increase the capacity by a fixed amount, so add some amount of memory each time, that becomes inefficient, right? If you're repeatedly adding elements to the to the list, then you end up calling add capacity too many times. You end up calling it O(n) times, and that becomes inefficient. Okay, so if the realloc succeeds, right, so check the pointer returned by realloc. Right, so if it's not null, go ahead and update the members of the list structure. Right, so the new capacity of T, right, is 2 times its old capacity. Right, the new array or the new pointer to an array for T is equal to new array. The size of the list doesn't change, right? We haven't modified the size at all. All that we've done is change the capacity, right? So we don't have to update the size. So we can return true at this point. And so now, whenever we need to change or increase the capacity of our list, we just call add capacity, and that simplifies implementing the remaining functions, like add. Right? So add is the function that adds an element to the end of the list. And so the first thing you want to test, right, is your list is full. Right? So if the size of the list is equal to the capacity of the array, then you know that we have to increase the capacity of the array. Right? How do you increase the capacity of the array? Just call add capacity. So we call add capacity, you test its return value, right? So if the return value is false, then we can't actually add the element to the list because we can't allocate memory for the new element. So we're going to return false. If you don't have to increase the capacity, or if you did have to increase the capacity and you were successful, all you have to do is go ahead and set the element at the end of the current list. Right? Now remember, the index of the element at the end of the list is size minus 1. Right? So the next element would be at index size. So go ahead and set the element at index size. Don't forget to increase the size of a list by 1, right? Because you just added an element to the list. And then you can go ahead and return true to indicate that add succeeded. Right? So once you've implemented add capacity, this is pretty straightforward. Insert is going to be similar, except we have to do a little bit of extra work. Right? So remember to insert into an array. Right? So I want to insert at index 4. Right? I have to move the elements at 5, 6, 7, and 8 one position to the right so that I can insert the new element. Right? So in other words, I have to take those elements shown in red shift them all over to the right. That frees up the spot at index 4, and now I can insert the element at index 4. Right, so I want to use a function that can move a chunk of memory one position to the right in this case. You could write a loop here too, if you wanted to, but it's easier just to call a function. All right, so for insert, also there's one more thing we need to talk about quickly. Insert's a bit funny because you are allowed to insert, well, we've decided that you're allowed to insert at the end of the list. Right, so it's legal to insert at index 10 in this case, right? Even though the last valid index for this list is 9. So we're going to allow insertion at the end. We're going to do it just by calling add, right? Because that's what add does anyway. Right, so if the index that the caller has passed in is equal to the size of the current list, go ahead and add the element to the end of the list, and do that by calling add. Right, add's going to take care of resizing the array if it has to. Right. Don't forget to return at this point because you don't want to. Right, if you forget to return at this point, we're going to end up adding the element twice, and you want to avoid doing that. Right. Again, we're adding an element to the list, so you might have to resize the array. So test is the size of the array equal to the capacity. If it is, increase the capacity of the list. Right. Finally, we're at the point where we have to move a bunch of elements one position to the right. Right. So you could write a loop here and do it on your own. Right. But it's almost certainly going to be faster to call one of the standard library functions that can move a block of memory. Right. And so the function that you want to use here is memmove. Right. So remember, there's two that we've been using so far, right? There's memcopy, which copies a block of memory into a new block of memory. And then there's memmove. So memmove will move a block of memory into another block of memory. The difference between the two is that with memmove, where you move the memory to can overlap with where the memory is coming from. Right? Memcopy, the memory can't be overlapping. You go back to the picture. Right? The memory that we're moving from, right? So we're going to move this block of memory here, one position to the right, right? And so notice that a bunch of elements overlap, right? So everything at 5, 6, and 7, and 8 overlaps with the new elements that are being moved over. Right, so here we're in the situation where where the source and destination blocks of memory overlap. We have to use memmove. If you use memcopy, it's not guaranteed that the copy will happen correctly. Okay, so how do you use memmove? It's very similar to how you use memcopy. Right, so memmove is the first one up here. Right, so it takes in a pointer to where you want to move the memory to. Right, so that's the destination. It takes in a pointer pointing at the start of where you want to move the memory from. Right, so that's from, that's to. Right, and it takes in the number of bytes of memory that you want to move. Right, so the number of that's just, yeah, so that's the size or the amount of memory that you want to move, measured in multiples of car. All right, so where do we want to move our memory from? Right, well, I want to move the element starting at the passed in index. Right, so I want, right, that's the element where I want to start moving from. Now I need a pointer to that element, so I'm going to take its address here. If you wanted to, you can just write T arrow ARR plus index, right? And that also gives you a pointer to the element at index in the array. Right, so either one's fine. I'm using the ampersand here just to emphasize the fact that we're taking an address here, right? You need a pointer. Where do you want to move the memory to? Well, I want to move it one position to the right, right? So I need a pointer that's one past index, right? Well, that's easy, right? I just use index plus 1, right? And take the address of that element. Right, so that's the element to the right. I want to take its address. Yeah.
It's just better.
Just index plus one?
Yeah.
No, you need to, let me copy it because I don't want to. Okay. So can you just write index plus one? Like that. So that doesn't work, right? Because index plus one is just some int, right? It's not actually an address. You can write T A R R plus. That you can write, right? So you need the start of the array or the start of the block of memory or a pointer to the first element, right? And then you can add the offset there. Yeah, so that's fine too. Yeah. And then finally, how much memory do you want to move? Well, I need to move some number of elements n, right? So back here, right? How many elements do I need to move? Well, the size of the list here is 9, right? I'm at index 4, and you can see that we have to move 5 elements, right? So it looks like the number of elements we need to move is just the size of the list minus the index. Right. So back to here, I computed the size, right? So the number of elements we need to move, well, it's just the size minus the index, right? How much memory do you need to move? How much memory do we want to move? I want to move n chunks of memory that are each that big, right? So n times size of int here, right? Again, because sizes are always measured in multiples of car in C. Let's remove that. Okay, so I've moved everything over one position to the right. So now I go ahead and insert our element, right? So I write into the element at index, right? Don't forget, increase the size of the array by the list by 1 because we just inserted an element, and then finally return true. If you really don't like, so you should learn how to use mem_move and mem_copy. They're not that hard to use, right? As long as you're comfortable with pointers, they're pretty easy to use. If you're really unhappy with this, you can always write a loop and move the elements yourself, right? That's the way we did it back in 124. So in 124, I avoided telling you that you can actually call a function that will move a chunk of memory. It's in the system if you're interested in how to do that. Removing an element is like inserting, except you're going to shuffle elements from the right over one position to the left, right? So if I want to remove an element somewhere, I guess we have the slides for this, so why don't we just look at the picture, right? So if I want to remove the element at index 4, right, I'm going to move the elements from indexes 5 and 10, one position to the left, right? So I'm going to take the elements in red, move them one position to the left. Obviously, we're going to use mem_move again. So for this remove function, I'm going to return the element that was removed. So I need to remember what is the current element at the specified index, right? How many elements do you need to move? Go look at the picture, do a little bit of arithmetic. You'll convince yourself pretty quickly that it's the size of the list minus the index minus 1 is the number of elements that you need to move, right? It's always useful to draw a picture somewhere and then figure out the computation based on the picture. Right. If you don't believe me, just go look at the picture and convince yourself this is true. Right. Okay, so if n is greater than 0, oh, sorry. Why is it? Oh, yes. Why am I checking is n greater than 0? That's a good question. Right. So it is possible for n to be 0 in this case. Right. So if you ask to remove the last element in the list, right, then I don't have to move anything. Right. I just leave the element there and then just decrease the size of the list by 1, right? And so it is possible for n to be 0. Now the question is can I pass in 0 to mem_move for the size? Right. The answer is where'd it go? Is it not documented here? I'm almost certain that n can't be 0. You end up with undefined behavior. Almost certain anyway. It's hard to remember all of these, the specification for all of these functions. Undefined, either just is invalid or null. I'm not going to Google for it. I'm pretty certain that you cannot pass in 0 safely here. right? So I'm going to make sure that if it is 0, I'm not going to do the move, right? If it's not 0, then I have to do the move, right? So once again, where am I moving from? Right. Well, I'm moving starting at the element that's 1 position to the right, right? So index plus 1, right? I want the element at index plus 1, and I want its address. Right. Where do I want to move to? Well, I want to move it to the element sitting at index, right? So element sitting at index, take its address, right? How many elements do I want to move? Well, again, it's oops, sorry, it's n elements, where n is the size of minus the index minus 1. Once you've moved that block of memory over, right, don't forget to update the size because we just removed 1 element from the list. Right. And then finally, we're going to return the element that was removed in this case. Right. And so those are the basic list functions. Right. You've got insertion, removal, you've got adding to the end. Right. And then you can add a bunch of other functions if you want. Right. So if you want to search the list for something, you can add in a contains function. Right. If you want to test if 2 lists are equal, you can add in an equals function. So on and so on and so on. Right. So I guess for programmers who come from Python and Java, it's always nice to be able to print out something. Right. If you're a C programmer, you generally tend to not do these sort of things. Right. So if you want a function that converts a list to a string, you try to implement one, but notice how long this thing is. Right. It gets pretty long pretty quickly. So I guess it's worth looking at this now. If you don't really understand what's going on here, don't be too concerned. Right, we're going to come back and look at the functions that I'm using in this piece of code later on anyway. Right, so I guess the take-home message for this is that it's not so easy to generate the string representation of something in C. Right, you've got the problems where I want to return a string, so I have to allocate an array. Right, that leads to the problem of, well, how big is the array? Right. Once you've figured out how big the array is, you've now got to figure out, well, how do I put the elements of the list into the array? Right? And so these are all things that you have to deal with. All right, so I'm going to start by checking the size of the array, the list, right? So if the list is empty, right, what I'm going to do is I'm going to return, so the list that I'm going to return looks the same as a Java list, right? You've got square brackets, the elements in the list with a comma and a space between them. Okay, so the list is empty. I need to return an array of size 3. 3, right? Opening square bracket, closing square bracket. However, this is a C-style string, so you have to put it in the null terminator as well. You need an array of size 3 to hold that. How do I make an array of size 3 that I can actually return from a function? Well, you have to dynamically allocate the array. Right. So we're going to call malloc in this case. Once I've got my array, I want to put in the elements. I want to write into the array the opening and closing square brackets. And so the way I'm going to do this here is I'm going to use sprintf. Right. We talked about sprintf in a previous lecture very briefly. Right. So remember, sprintf is just like printf. Right. Printf prints something to standard output. Sprintf prints something to a string. Right. And so it works more or less the same way. You've got conversion specifiers, and then you've got the receiving arguments. So here I want to print into the string s, right? And I want to print that stuff into the string, right? So here there's no conversion needed, where I'm just going to print some characters into a string. You wanted to, you could go into s and set the elements manually, right? So in other words, you could write S0. But, oops, sorry, S0 is the opening square bracket. Oh, wait, right? S1 is the closing square bracket, right? And then S2 is the null terminator. Like that, right? So you could do that instead, and that would be perfectly fine, right? But you have to remember, you have to write in the null terminator, right? If you don't write in that null terminator there, bad things could happen, right? You don't have a correctly terminated string. Right, so that's perfectly fine if you wanted to write it that way. The string is short enough that you could write it this way. Sprintf is easier though, right? It's one function call. It's a pretty important function call. It's used quite commonly, right? It writes in the null terminator for you. as long as you remember to make sure you had space in the array so that it can actually write in that terminator. All right, now the next problem. So if the list is not empty, then it's got a bunch of, it has at least one int in it, right? And now you have the problem of how much space do I need to write an int into this array, right? The other problem you have is that you don't know what you don't know ahead of time what all the ints are in your array, right? So you could have the int 1, could have the int 1 billion, right? In one case you need 1 character, in the other case you need 9. And then furthermore in C, you don't actually know how big an int is, right? You don't know what the maximum size of your int is. You don't know ahead of time there's no fixed size for an int in C, right? And so you have to compute what is the size of an int in C. So the way I'm going to do this is I'm going to allocate a chunk of memory that can hold a list where all the elements of the list are the longest possible ints. So what I'm going to do is I'm going to compute what is the longest possible int for my particular computer. Right. So I'm going to start with a temporary array. So it's called temp. It's 100, which is almost certainly bigger than, that's almost certainly enough characters to hold the digits of the largest int. Right. If it's not, then I've got other problems, right? 100 digits is huge. So that's almost certainly going to hold the largest possible int. I'm going to print the largest int on my machine into that temporary array. Right. So int min, int min is the name of the, oh yes, right. One other factor here, right? Remember that the longest int on your computer is a negative value, right? Because there's negative signs in the number, right? So you actually want, so the longest possible int in terms of the number of characters needed to print it, right, corresponds to int min, right? The most negative integer value that you can hold on this particular computer. Right, so I'm going to print that number into temp, and then I'm going to figure out how long is that number. The function string length, which we haven't seen yet, will tell you the length of a string, right? So the length of a null terminated string in C, right? It gives you the number of characters, not including the null terminator of the string. So I can get the length of that number when I print it out using string length. Right, so max int length, that's the length of the longest possible int when you write it out on my computer. All right, so now how long does my array need to be? Right. So I've got I have size of these things. Right. Now every time I print out an int, I want a comma and a space after it. Right. So every time I print out an int, I need at least that many characters. Right. So max int length to hold the int, +2 for the comma and the space. Right. And I need that many in total. Right, and now I'm going to add 2. So this number 2 is not the exact number here, right? So I need some extra. I need 2 for the opening and closing square bracket, right? And don't forget the null terminator, right? I don't need the null terminator because I added 2 to every number. But don't forget that you don't need. So the reason I have that is because of that comma space here. But don't forget that the last thing that you print, the list, doesn't have the comma space. Right. So I already have an extra 2 characters available to me. So I don't have to add the extra 1 here for the null terminator. Right. I have enough. Right. So technically you could add 1 here and you would be just fine. Notice that this is very tedious and exhausting, right? And very error prone as well. This is not something you want to do regularly in C. All right, finally, how do I write this thing into my array? Remember, S is the array that I'm writing into, right? So I'm going to start by creating a pointer P. I'm going to set that to S. So P is pointing at the first character of my string. I'm now going to print each character into the array. Right, so I'm going to use sprintf. Now remember, what does sprintf need? It needs the start of where I want to write something into the array. Right? So for the first element, or for the opening bracket, I want to start writing at the front of S. So P is going to be my pointer that keeps track of where am I in this array. There's my array. P is going to keep track of where am I after I printed everything that when I print each thing that I need to into the array, P is going to point to where is the next free location in that array. Okay, so we start by pointing at the front. I want to write the first element. I want to write the square bracket followed by the first element of the list into the array. Okay, so square bracket. Right, I want to write the first element. So the first element is an int. So I'm going to use %d for the conversion. Right, now I have to tell sprintf what am I printing? So I'm printing the first element into the array. Right, so that's an int, gets converted with %d into a string. Right, and we got the opening square bracket. So that's going to do something like right, square bracket, and let's suppose that our number is 0. Sprintf returns the number of characters that it writes. So in this case, it's going to return 2. Right? I wrote, so it's going to tell you, hey, I just wrote 2 characters into this array. Right? I now need to shift P to the next free spot. Right? Because the next thing that I want to print is going to start there. Right? So I need to shift P over to here. Right? Like that. So that's P plus 2. So move P to 2 places to the right, or in this case, move P n positions to the right. Right, and now I just want to repeat this process, printing out comma, a space, and the next element in the list. Right, so print. Right, all the remaining elements with a comma and a space in front of them. Right, so it's the same thing all over again, right? I'm going to use sprintf. Right, I'm going to use P to indicate where am I printing into the array. Right, what do I want to print? I want to print a comma and a space followed by an int. So comma space %d. What do I want to print? I want to print the ith element of the array. Right, every time you print something, remember how many characters did you print, and then shift the pointer n positions to the right each time. Right, once you've done that, you've printed all the elements of the array. You can print the closing square bracket. Right. Sprintf also appends the null terminator every time it does something, so we're good there. Finally, you've got your string. You can go ahead and return S. Right. So notice this is much more complicated than what you would have to write in either Python or Java. Right. So Python and Java, they because of the way their string classes work, right, they take care of all this extra memory allocation for you. Right. So notice what's going on here. Right. The other way to write this is that you could start out with an array of size 0. And then expand the array every time you printed something into the array. Right. So in other words, you could make a list of characters, right? And then let your list of character class deal with the resizing of the array each time. Right. And so that's the way things work in in Python and Java. Right. Their string classes will expand the size of the underlying storage when you create longer strings. Right. In C, so you could do the same thing in C. Right, if you really wanted to. So there are other ways to write this function, right? But again, notice that it's not so straightforward to actually generate the string representation in this case. Right. There's another way to do this. So there's a second version of the function. I don't want to take time to look at this second implementation. Right. So I'm just going to use the first. We'll leave this topic just by showing just with the first list string function. There's one more thing we need to talk about. It's how you have to clean up after yourself in C, right? So if you dynamically allocate something in C, when you're done with that object, you have to release the memory that was allocated that you allocated, right? So the functions that we had to create a list right? The init functions, right? They all do 2 mallocs actually, right? So they allocate room for the structure, right? So that's the first malloc, and then they allocate room for the array, right? When you're done with the list, you have to release the memory that you allocated for the array, and then you have to release the memory that you allocated for the structure, right? And you have to do things, in this particular case, you have to do them in the reverse order, right? If you release the memory allocated to the structure, right, then you don't have a pointer to the structure anymore, so you can't get to the array belonging to that structure, right? So deallocate the array, then deallocate the structure. So back here, right, when you are done with the list, or when the user is done with the list, they're going to pass in the list T, right? And you're going to free the array that belongs to the list T, right? I just have to go back to the header file and see what I specified here. Okay, so we're missing the one step here, right? So I want to deallocate memory that I allocated for the array, and then finally I want to free the pointer T as well, in this case, right? So that deallocates the array. And the next one deallocates so that's the correct implementation there, right? So when the user is done with their list, they call list free. List free deallocates all the memory associated with the list, right? Notice that the user can't do this themselves, right? The reason they can't do this themselves is because they don't know that the array, that this thing T has this thing called ARR inside of it, right? So remember back, if you look in the header file, so whoever's using this header file, they don't actually see what's in the structure, right? All they have here is this type def that says list is this thing that's a struct list, right? They don't know what's inside the structure itself, right? The only thing that knows what's inside the structure itself is the list itself, right? And so you need this free function here so that the list can deallocate the memory that it allocated for its array. All right, so that's the implementation. Well, I guess that's the partial implementation of a list of an array-based list in C. Any questions about what's going on here, right? So it has some similarities to the list that you saw in 124, right? The differences are all related to handling memory. Right, so when you allocate an array, right, you're using malloc. Sorry, when you're creating a list, right, you're using malloc to allocate space for the structure. You're using malloc to allocate space for the array, right? When you're done with the list, right, you have to remember to free the memory that's allocated to the array and free memory that's allocated to the structure. Right, Python and Java, they take care of this thing here for you, right? They use some technique or techniques that can detect whether or not an object is needed or is still needed by your program. When they're not needed, they get marked and they get removed automatically, right? You don't have that luxury in C. All right, so if there's no questions, I'm going to move on and introduce the next topic. And so that's going to be implementing. So we're going to do two things. We're going to implement a data structure where instead of using an array, we're going to use a linked sequence of nodes. Right? We also did that in 124. Now you're going to see the C implementation. We're also going to implement a structure where you can hold not just ints, but you can hold any type. Right? And so I'm going to do that by implementing a stack. Okay. So everybody remember what a stack is, right? It's just a stack of stuff. Right? In a stack, classically, you can only do something with the top of the stack, right? So you've got access to that element there, and that's all that you have. If you want to get something out of the stack, if you want to add something to a stack, you push onto the stack, right? To get something out of the stack, you pop, right? And that affects the top element, right? So pushing onto a stack, Right, we're going to push the 1 onto the stack, then a 2, then a 3, then a 4, then a 5. Right, notice that if you remember 124, right? I guess if you're in 124 this term, we haven't gotten there yet. So is anybody here in 124 right now? Right, there's at least a few people. All right, so I can't go that fast. So that's the problem with this course, is that you can be in 124 and not have taken this, not seen a stack yet. So I was going to say, if you've taken 124, when you push something, you just push the element. In C, right, you have to tell the C function what stack are you pushing onto. Right, so here we're going to be pushing onto the stack ST. Right, so when you push a 1 onto the stack, let me reverse this. Okay. Start with the empty stack, push a 1. There's a 1 on top of the stack. Right, you push a 2, the 2 now becomes the top of the stack. The 1 is the next element of the stack. Right. Push a 3, the 3 becomes the top, the 2 and the 1. Conceptually, they move down. Right, so on and so on. Right, when you pop an element from the stack, you're going to remove the top element from the stack and return it back to the caller. Right, so if I pop the 5 off the top of the stack ST, right, you end up with the number 5. Right, X becomes 5, then it becomes 4, and 3, and 2, 1. Right, and now you have an empty stack again. Right, stacks are widely used in computer science and engineering. Right, so again, if you're in 124, you would have seen this already. Right, stacks are often used for undo and redo operations. Right, so whenever you're undoing or redoing something on your computer, you go to your edit menu and you hit undo. There's a good chance that the way that functionality has been implemented is with a stack, right? So whenever you do something, you push it onto a stack, right? Whenever you want to undo something, you just pop that element off the stack and undo whatever that operation was. This is a silly example of using a stack for something, right? So if you have an array, you can reverse the elements of the array using a stack. Right, you can also reverse the elements of the array manually, right? But if you wanted to, you can make a stack. Right. So to reverse an array, ARR, I'm going to make a stack. I'm going to push each element of the array onto the stack. I'm going to pop all the elements off the stack. Every time I pop, I'm just going to put it back into the array. Right. Don't forget to free the stack once you're done with it. Right. So in a picture, if that's my array, right, and here's my stack, I'm going to start adding the elements of the array onto the stack. Right. So I'm going to add the 1 on the stack. I'm going to add the 2, and I'm going to add the 3. Right. I'm now going to pop the stack. Every time I pop the stack, I'm going to put it back into the array. Right. So I'm going to pop 3 off. I'm going to write that into the first element. Right. I'm going to pop the 2 off. I'm going to write that into the second element. That's a typo. Right. I'm going to pop the 1 off and write that element into the array. Right. And that reverses the array. Right. This works because of the nature of the stack. Right. So the stack is what's called a LIFO. So last in, first out data structure. Right. The last element you push onto the stack is the first thing to come out. Okay. So you could implement this with an array. Basically, it's going to look exactly the same thing as a list. Right. You have to adjust how pop and push work. Right. If you implement it with an array, then you have to deal with the fact that when the array becomes full, you have to reallocate the array, right? And that's an ON operation, right? So pop, if you use an array, is always O1, right? All you're doing is you're getting an element out of the array, right? Push, unfortunately, becomes ON in the worst case, right? When the underlying array becomes full, you have to reallocate and copy the array, right? So that becomes ON. If you use what's called a linked-based structure, right, you get O1 guaranteed complexity for both push and pop. Okay, so what we're going to do here is we're going to use a sequence of nodes to implement this the stack. Right. So in other words, every element is going to be held in its own little structure. If you've all taken your what's it called 204, right? By this point in time, yes. So you've all seen trees and other things, right? Like that. So you've seen this sort of structure before called a node. So in a node, you're going to hold, well, conceptually, you can hold an element, right? So one value. And then you can hold in C, you'll hold a pointer to 0 or more other nodes, right? And those pointers are usually called links. So for a stack, we've got a linear arrangement of nodes. You're starting at the top. The next element after the top node is the second node, right? Then you have a third node, and then you have a bottom node, right? So each element you can think of as being connected to the next element deeper in the stack. So what we're going to do is we're going to create a structure for this thing here, right? So our structure is going to have room to hold an element, right? And then it's going to have a pointer that points at the next node in the sequence. So if you've got a stack of size 1, right? You've got one node, and then there's no next node, right? So that pointer is going to be null. So there's your element. That pointer is called a link. If you want to push something on top of the stack, I make a new structure, right? I make a new node, copy the element into the node, right? And then set the link so that it points at the current top of the stack. Right? So I'm going to set this pointer so that it points at the current top node. Right? Now I've got a new top node, so I'm going to adjust this pointer so that it points at the new node here. Right? If you're keeping track of the size of the stack, you want to increase the size of the stack by 1. To pop an element off the stack, right? I've got a pointer to the top node. Right? Oops, sorry. I want to remember what that value is, because I want to return this 3 back to the caller. Right, so I'm going to remember what the 3 is. I'm going to adjust this pointer so that it points at the next node. Right, now how do I get to the next node? Well, this node has a link or a pointer to the next node. Right, so I'm going to ask this node for its next link, right, and set that to top. Sorry, set top to that value. And then I have to get rid of this node, right? So to get rid of this node, remember that to make a new node, we allocated memory for a new node, right? So we called malloc or something to get a new node, right? Once I've popped something off the stack, I now have to remember I have to deallocate the memory that I allocated for the node. So we have to free the memory that's associated with that node. Right, again, that's something we didn't have to do in Java because Java gets rid of the memory for us. Right, and then finally, don't forget to update the size of the stack. All right, so in the next lecture, we'll look at how you implement this thing very quickly, and I'll show you how you can actually implement a generic stack in C.